me 10-15 seconds.
Ciao Alberto, benvenuto.
Ciao a tutti. Hello everyone.
Good morning.
Good morning.
Great to meet you again at a different venue. Sooner or later, we'll get to know each other in person. Are you a boxer? Alberto, you're a boxer?
No.
No?
Okay, Stefano, we are live. We're live on streaming, yes, Stefano. So we are live now. You can start.
Okay. Alberto, you're a boxer?
No.
No?
I heard my hand whipping cream, so like just need to.
Yes, that's a gentler activity, a less aggressive one.
So we are live now.
But I thought it was a Leone thing, a Leone rap.
No.
No, it is like a martial arts rap, but it's like it's what I had home. So.
Oh, I see. I see.
I heard my hand whipping cream, so like just need to.
It's a gentler activity, a less aggressive one.
So we are live now.
But I thought I hear my voice with several seconds delay.
Yeah, it's okay. It's the streaming because I had the volume on. Now I turn it off.
I see.
You can start anyway.
Okay. I don't know how to start. I would say good morning, but it may as well be good afternoon, good night, good whatever. Good day, everyone. And welcome to this first online edition of Quantum ESPRESSO School. I am thrilled, as I was saying to my colleagues before switching the microphones on, because this is the very first time we go live online. And it's an experiment for everyone. Of course, this gives us the opportunity to reach out to many of you all over the world, but it also leaves some uncertainties. And I beg you in advance to forgive us if anything does not go as smoothly as we wish it will. This is the 25th edition of a long series of schools that started at ICTP in 2001. Since this school has roamed many continents around the world, including Europe, of course, the Americas, both North and Latin America, Asia and Africa. You guys and girls have been preceded by almost 2,000 previous participants in this series of schools. This time we had an immense and unexpected success. We received 1,300 applications from 92 countries. and 123 such applications have been selected. We apologize to all those who had to be excluded. Probably in the future, we will admit more people than just the 100 that we have admitted this time. But we wanted to make sure that for this first time we can manage hands-on rooms, hands-on sessions in as smooth a way as possible. This school should have taken place in person in 2020 in Shanghai. And I wish to thank Professor Ray from Shanghai University for volunteering to host the school last year, and Alessandro Stroppa for putting us in contact with Ray, with Professor Ray and the University of Shanghai. Unfortunately, as you can imagine, the pandemic prevented us to make it last year. And it took us some time to figure out how to proceed. We hoped, we have been hoping for a while to make it in person, but at the end, I have no regrets. I mean, at the end, as much pain the pandemic may have given to all of us, but this, I think, prompting us to try this experiment is one of the few good side effects of the pandemic. So no regrets about that. The last edition of the school was held in person in Ljubljana in 2019, and it was a success. I wish to thank Tore Kokal and his collaborators for hosting us in the Josef Stefan Institute in Ljubljana in 2019, and for the incredible work they made to make this virtual edition a success, I'm sure. So there's the school is the result of a long collaboration between CISA and ICTP in many areas of research and education, and it is being held under the umbrella of two parent institutions that I would like to acknowledge. You may wonder what MaX means. MaX is an European Center of Excellence for Supercomputing Applications. That is the main source of funding for the Quantum ESPRESSO project these days. Many distinguished institutions from all over Europe belong to MaX, including CISA, ICTP, the Italian National Council for Research, the EPFL, the School of Technology in Lausanne, the ETH, the School of Technology in Zurich, Forschungszentrum in Jülich, CEA in France, the Catalan Institute of Nanoscience and Nanotechnology in Catalonia, in Spain, and communication and dissemination is also being taken care of by the Ghent University, SICAM, and the Trusted Service Company. The Quantum ESPRESSO Foundation is the home of the Quantum ESPRESSO project itself. It's an institution that is being supported by CISA, ICTP, EPFL again, the Cineca Supercomputing Center in in Bologna, the University of Texas at Austin, and shortly, I believe and I wholeheartedly hope the Joseph Stefan Institute in Ljubljana. I would like to cut the long story short and proceed with the acknowledgement of the many people and institutions which have made this event possible and his preparation incredibly smooth. I'm really grateful to the local organizers, the two Ivan Girotto from the ICTP and Ivan Carnimeo from CISA, whose energy and constructiveness has been really instrumental for the success of the preparation. The efficacy of the ICTP staff, both administrative and technical, has been beyond imagination as usual. And I would like to present my own personal thanks and the thanks of all the organizing committee to Adriana Pinto and Massimo Maffione, who is assisting us in this very moment. Hardware resources have been provided by a range of different public and private bodies, and our thanks goes to all of them as well. I won't forget any of these important sponsoring components, which include several computing centers, Cineca, Arnes, that's an organization for research in Slovenia, the HZW company in the Far East, in the Shanghai area. ICTP and CISA are providing their computational support as well. I'm sure I have forgotten some important thing, and apologize in advance to anybody or any institution that I may have forgotten to thank. My wholehearted thanks goes to those whom I have forgotten as well. So I wish all of you to learn as much as you can teach, and to enjoy this school as much as we will enjoy it. Thank you very much for being with us, and I leave the stage to Raf de Bauer.
Okay, thank you very much, Stefano. I hope that everyone can hear me. So welcome also from my side. My name is Ralf Gebauer. I'm from ICTP. And before starting, I should say that it's obviously a big pleasure and also a big honor to be the first speaker in this long 2 weeks event. And I should also say this should really not be my place now to speak, because everyone who knows something about Quantum ESPRESSO and about the community behind it immediately knows that one of the pillars of everything which we'll be hearing about in these 2 weeks is Paolo Giannozzi. And so it was planned in the original program that this first talk would be given by Paolo. And so by all means, he should be the first speaker and introduce everyone to Quantum ESPRESSO, which he is very much under the pillars of it, as I just said. Okay, so Paolo cannot come today. You will all meet him tomorrow when he will give a talk. So it's just 1 day later. And I will now try to share my screen in order to start the presentation. Okay, so I hope that you can see my screen now. Please interrupt me when if something goes wrong with the presentation or so. So my plan today is to give you a very general overview of what Quantum ESPRESSO is. And I will spend most of the time of my talk then, in fact, talking about very basic things. Mainly, I will talk about the plane wave basis set and what plane waves and periodic system and K-points and all these kind of things have to do one with the other, because these are very recurring themes which also distinguish Quantum ESPRESSO from many other electronic structure codes. And I think as a first presentation in this conference, this is probably the main topic one should mention. As Stefano has just said, we have had many kind of schools in the past, but this is really the first one where everything is virtual. And this being virtual, this is really a very large-scale collaboration. Here I just list the logos of kind of sponsors, and you see all kind of different institutions. There is the Quantum ESPRESSO Foundation, obviously. There's MaX, which Stefano has just introduced. There are also the two Trieste institutions, CISA and ICTP, which is my own affiliation. There's SECAM. We have supercomputer centers, Ginega from Italy. There is the Arnes Supercomputer Center, which is in Slovenia. We have Shanghai University. So it's really a large-scale collaboration by many people, just like Quantum ESPRESSO itself is a large-scale collaboration of many developers, many interested people, and so on. So this is where I am in this very moment. This is Trieste, the Miramare region. I am sitting right now in an office which is somewhere here in this building. And if there wasn't this horrible pandemic going on, I think it's quite sure to say that we all would now be here in that area and sitting somewhere close to the seaside and talking about physics. But well, we all know that it could not come like this. So only I am here now, and I'm trying to talk to all of you from all kind of places in the world. So let me just say some words about ICTP, since this is my own institution. So ICTP is, we have just seen where it's located, here in Trieste. It is now nearly 60 years old already, and it was founded by the Nobel laureate Abdus Salam. And we are, in fact, an international organization which is under the two United Nations agencies, which are UNESCO, so the UN arm for science, culture, and education, and the IAEA, which is the International Atomic Energy Agency. And we are also regularized by the seed agreement with Italy. So our goal in ICTP is to bring together people from everywhere in the world to do science and work collaboratively on scientific problems. We all know that in today's world, more often people do wars against each other than do scientific collaboration. So I think this mission, even now 60 years after the foundation of our center, is very important. And in a sense, this going virtual, like we are doing now with this school and so on, these virtual ideas also are kind of bringing us close to our to this mission of bringing people from the whole world together. This is very well illustrated if you look at this map of the world, where these circles here indicate where people have been applying from. And you see really from every corner of the world, we have had applicants. In fact, this activity is a record breaker. Never in the history of ICTP, anything has had 1,292 applicants. So we are very proud of this, obviously, this big success and interest which Quantum ESPRESSO and which our topics have. I would also like to say what Stefano has already said. We are at the same time very sorry that this 1,292 is about one order of magnitude more than the number of people we could admit. The reason is that this is a hands-on school and we have a limited number of tutors and it's the first time, so we could really admit only many fewer people than we would have liked to admit. So I would like to say to all those who have not been selected and will perhaps now look at this on YouTube in streaming or watch a recording later, it is clearly not due to you that we could not admit it, but it is the logistics and the fact that it's the first time. So I would like to go to science and not say many thanks, but this huge number of applicants and this fact that this is really first for ICTP, this has put a lot of work, especially on the secretaries who had to deal with all these applicants and so on. So I would like just here say a special thank to Monica, Victoria, and Adriana, who have in a very nice and smooth way managed to cope with so many applicants and so much bureaucratic issues. Okay. So again, this thing. Okay. So I would now like to come to the heart and to the star of this school, which is Quantum ESPRESSO. Okay. So what does this Quantum ESPRESSO mean? Well, so at quantum, everyone knows what it means because we're doing quantum mechanical simulations. And this ESPRESSO stands for Open Source Package for Open Source Package for Research in Electronic Structure, Simulation, and Optimization. This is an acronym which we have been looking a long time until we found something. The real reason is probably that most of the people behind Quantum ESPRESSO are Italians. So that might be one of the reasons why this is called espresso. The other reason might be that the results you get from these calculations, they are so exciting that it's like an espresso. It keeps you excited and awake when you use Quantum ESPRESSO. And so Quantum ESPRESSO, as we talk about it today, exists in fact since 2002. And since this is an activity which we are doing together here with a Chinese organization, I would like to recall the fact that, in fact, in this year, 2002, many of us were sitting in Beijing airport, and we were precisely discussing that the set of programs and codes which already existed, but which did not really have neither a trademark nor a real structuring beneath them, they should come under one umbrella. And it was, in fact, in Beijing airport that the name espresso for this whole thing came up. So this is also some connection to China. And so in 2002, this umbrella was kind of created, Quantum ESPRESSO, but some of the core components or the most important components which underlie many of these codes, this goes back more than even 30 years, and probably even more than 30 years. But since 2002, there was this deliberate effort to try to put subroutines in common between different programs to have a common architecture for many things which before were very different. And what distinguishes this Quantum ESPRESSO from many other approaches to electronic structure is that we are not always mentioning, but we are trying very much to be at the forefront of theoretical methods. So when someone invents new functionals or a new computational method to calculate something new, very often, rather quickly, these new developments find their way into Quantum ESPRESSO. And so we are kind of proud of the fact that most of the interesting things today are, in fact, in one way or another implemented in Quantum ESPRESSO. So one of the two goals we have is this staying close to innovation. And the other goal is that we are trying to make these codes run on as many different computer architectures as possible. Some of you have perhaps already seen this video which Nicola Mazzari has once done, where he has installed a Quantum ESPRESSO on a smartphone. It was even a very old smartphone. So basically from smartphones up to mainframe computers, clusters, your laptop, you name it, Quantum ESPRESSO can use and run on many modern architectures, including architectures which have accelerators and so on. There will be also some session about GPU and accelerators, in fact, in this school. Okay? So these are the kind of the two aspects which I would say distinguish us from many other things. Another thing which is not particular to Quantum ESPRESSO, but which I find extremely important, is that this code is a free code. Okay, so everything in Quantum ESPRESSO is distributed under this GNU public license. And this means that anyone who wants has access to the source code, but not only has access to and can read it, but can also distribute the code however someone wants. So if you take Quantum ESPRESSO and you find someone who's even willing to pay you money for giving it, you can even sell the code if you want. It's completely free. The only thing is that this license requires that if you have some derivative work related on it, you are asked also to publish this under the similar kind of license. Okay? And this kind of free nature of our codes, it not only means that everyone can use the code, even if people working in some research groups which perhaps do not have the money to pay licenses or so on, but it also means that people who perhaps like programming or like new methods, they have a very low hurdle to overcome to implement their ideas in our codes. This is probably also one, so I think this free license is also one of the reasons why we are able to stay, as I said, in the forefront of new developments and having all the time new developers which are joining our team. Obviously, I mean, this free license is not singular to Quantum ESPRESSO. I mean, the most famous one is the Linux kernel, which is in this very moment running on most of your computers. So another thing which I should say in the beginning is, if you're really a beginner and you wonder, where can I get more help, or where can I get answers to my question, and where can I get information from? There are various sources which you can look at. Well, one is obviously a school like this one. You can look at this school, and you can also look at recordings of previous schools where many things are explained. But apart from this, one of the thing is obviously the official documenting papers. Here, these two papers from 2009 and 2017. And in fact, we are very happy if people who have some results publish some results with our codes, if they cite these papers. Another very rich source of information is obviously our website, quantumespresso.org. On that website, you can find links to the code itself. You can find links to pseudopotentials, to various places where pseudopotentials can come from. You can find links to mailing lists. So this is kind of probably the first place to start looking for information, is this Quantum ESPRESSO website. Now, this week, all of you will be working with the code itself installed in a computer. And as soon as you install Quantum ESPRESSO on your computer, you will have all the source code, obviously, but also the source code contains this documentation, these doc subdirectories, and they contain a lot of input explanation and files which explain you how you can address certain problems. If you're more not so much into a user, but into a developer's one, then you might be interested in the GitHub, obviously, where Quantum ESPRESSO is hosted. And then if you run Quantum ESPRESSO and something stops with some cryptic error message, which we really don't know what it means, one good thing is always to look in the archive of the mailing lists. So copy the strange error message in Google or so, you will very likely end up on these mailing lists, which I recommend you to subscribe. And if you do not find in the archive of the mailing list the answer to your problems, then you can obviously also write to the mailing list. And there are many people who try to help with these issues. So there are many ways how you can get help. Or I mean, if you're lucky and you know some of the people and tutors of the next 2 weeks, you may also contact one of these people directly, obviously. Then I should a bit say what Quantum ESPRESSO itself is. So Quantum ESPRESSO, in fact, is not one code. Okay, so you cannot go on a computer and say, run the executable Quantum ESPRESSO. In fact, this does not exist. There is no executable Quantum ESPRESSO. Quantum ESPRESSO is kind of, as I said before, a package. It's a package which contains various other codes, many other codes, as you will see in a second. And but these packages they rely on two packages which are the core of everything, and also kind of the oldest one. One is the PW program. It's pw.x is the executable. We call it PW-SCF. It stands for plane wave self-consistent field. This is the main workhorse for calculating the electronic structure in a self-consistent way. You can do structural optimizations of your system. You can use variable cells. PW-SCF can also do molecular dynamics to some degrees, but it's really not optimized for being very fast in molecular dynamics. For molecular dynamics, instead, there is this second basic code, which is the CP code, the Kappa Marinello molecular dynamics. And as the name indicates, the CP code, this is really geared to do Ab-initio molecular dynamics. And it can also do variable cell molecular dynamics. So these are the two basic codes, and it's very likely that for running any of the other codes or for using any of the other codes, you will probably first have to run either PWSCF or CP in order to get the basic results on which then the other codes rely. So here I just made a list, and I'm sure I might have forgotten some. So the most important kind of other codes which are part of this distribution. So on one hand, the phonon code. It's also one of the oldest codes which of the package. This implements linear response calculation, so density functional response theory. And with this code, one can calculate phonons in the system and dielectric properties. And so this is a typical thing here to calculate in a system phonons. One first has always to calculate with PWSF, the ground state electronic structure of a system. And then kind of as a second step, one can run phonon or one of the other codes, then to calculate, in this case, the phonons. Another big part of the things are the PP programs. PP stands for post-processing. And this allows you to analyze results you got. You can look at what is the density of states, how do the Kohn-Sham orbitals look like, what is the electrostatic potential in your system, things like this. So the PP programs allow you to examine and analyze results of, for example, PWSCF. Needless to say that during these 2 weeks, you will get in touch with with most of these codes, but certainly you will get in touch with phonon and the PP codes. Another very popular code is the NAB code, which allows you to calculate reaction pathways, transition states, and so on, reaction barriers. So this is a driver code which inside itself runs PW. Then we have the atomic suite of programs. So with the atomic code, one can create pseudopotentials, which I will talk about a bit later today also, what might be pseudopotential. So we have a code which is running for any given atom of the periodic table. You calculate the all electron atomic wave functions, and then you can create pseudopotentials. There is a GUI program also, which is a graphical user interface. There's a code PW-cont for calculating conductance. You can calculate X-ray absorption spectra with the X-spectra code. One can go beyond ground state electronic structure by doing either GW calculations, so many body perturbation theory, and we have one implementation of it which uses localized Wannier function. This is the GWL code. There is TD-DFT implemented, so time-dependent density functional theory. This is also a code which can be used for calculating electronic excited states. Something which in recent years has become extremely popular in the scientific community is electron phonon effects. So there is a code which is called EPW, electron phonon physics. This code, obviously, like the other one, is linked to the phonon code, which is linked to PW. So you see that there's also a hierarchy always of these different codes. And there's a code HP, which allows one to calculate some Hubbard parameters in certain systems. I'm sure that there are many more and other codes, but I think these are the most important. So you see, this Quantum ESPRESSO is not one code, but it's a whole distribution of different codes, which have a hierarchy because some of them need the output of one code in order to be run and to be analyzed. Okay, so this is kind of what Quantum ESPRESSO is really all about. And what is underlying everything is obviously the big theory is density function theory. Okay? So in this talk, it's just one talk today. I will not be able to give a full introduction into density function theory and explain where everything comes from. What I would like to do in the next minutes is, rather than really giving a full introduction to DFT, I will introduce the most important notation and just say the most important things, hoping that all of you have in one way or the other already encountered density function theory. So in DFT, so it's a ground state theory, we are interested in a system which has n electrons. Each electron has obviously a spin 1/2. And these n electrons are somehow distributed in space and give rise to an electron density. Now, the electron density is a very easy quantity because the electron density is simply a scalar function at each point in space. It's always non-negative. And the integral over all space of this density must correspond to the number of electrons you have. So the density, which is kind of our basic variable in DFT, is a very easy quantity, and surely much easier quantity than, say, the ground state many-body wave function of your system. Now, in DFT, what we know, thanks to Hohenberg and Kohn and the Hohenberg and Kohn theorem, is that there exists a functional, so a function of a function, which takes as an input this ground state electron density and gives you the ground state energy of your system. So this DFT functional is unknown, but one knows in a mathematical proven way that this functional exists. Okay, so the way how one addresses then this problem is typically going to the Kohn-Sham formalism. And in the Kohn-Sham formalism, this unknown functional of DFT is written as the sum of several terms. One is a kinetic energy term, this Ts, which you see here, then an external energy term, the Hartree energy term, exchange correlation energy, all these depend on the density, and then the trivial ionic interaction, which is just the Coulomb interaction between. So this here should give you the ground state energy of a system with charge density n. And you see, however, that Kohn and Sham, they had to introduce, in order to get a good approximation for the kinetic energy, they have introduced here orbitals. So not many body wave functions, but single particle orbitals, the so-called Kohn-Sham orbitals. And these orbitals, they are linked to the charge density just in the way as one would guess. So they are n orthonormal orbitals, and the sum of their square moduli, this is the famous charge density. They have introduced these orthonormal Kohn-Sham orbitals in order to have a good approximation for the kinetic energy. So this Kohn-Sham non-interacting particle kinetic energy is written in the following way. So it's again a sum over all these n Kohn-Sham orbitals, and then the usual expression one would write for kinetic energy. Okay? And these orbitals, obviously, they are n, and they are orthonormal. This is obviously not the exact kinetic energy of a many-body system. It's an approximation. This is why it's so T, but it's Ts, the single particle kinetic energy. And all which we do not know about this functional, in fact, is hidden here in this exchange correlation functional. All the other energies, in fact, we can write them down explicitly. So the external energy, so external means coming from the ions. It's simply the external potential, which is the Coulomb potential due to the atomic nuclei, which are positively charged, exerting on the electrons. So this here is simply the density times the given external potential. The Hartree potential is also very easy to write down knowing the density, because it's simply the classical Coulomb interaction of charges. So written here in this way. Ions, as I've said, is simply the pointwise interaction between the ions of your system. The big unknown in DFT, and the problem where kind of the failures of DFT come in, is that no one knows the exact form of exchange and correlation. Okay, so this exchange correlation functional must be approximated, and there are many various approximations. None of them is perfect. I will in this talk not talk at all about exchange correlation functionals, but the usual ones, which either simply are local approximation in terms of n, or semi-local, or then also more complex stuff, are implemented, in fact, in Quantum ESPRESSO. So for the moment here, just take for granted that some approximation of the unknown energy here, the exchange correlation, is given, and we take that in our code. So this gives us now a way of writing the ground state density of our system in terms of, say, either density or these orthonormal Kohn-Sham orbitals. So in practice, what is always done is one wants to find the ground state energy. So one is minimizing this quantity with respect to the density, or if you want, with respect to the Kohn-Sham orbitals. And if you write down, in fact, the functional derivative of the DFT energy with respect to the Kohn-Sham orbitals, and you add the constraint that these orbitals must remain always orthonormal, then one ends up with an equation which looks like this. These are the famous Kohn-Sham equations, and they look like a Schrödinger equation. Okay? So the Kohn-Sham equations are essentially a Hamiltonian-like operator acting on each one of these single particle Kohn-Sham orbitals equals energy times this. So a Schrödinger-like equation. And this Kohn-Sham Hamiltonian, which we have here, contains, in fact, the derivatives of the energies we have seen before. kinetic part, which is simply the derivative of the kinetic energy of the previous slide, the external potential, which is due to the nuclei, the Hartree potential, and exchange correlation potential. And the formal definition is that the exchange correlation potential is the functional derivative of this unknown exchange correlation function with respect to the density. Same for Hartree, it's the functional derivative of the Hartree energy, which we know explicitly, and therefore it has this easy form. And so one can solve this equation. So you have a Schrödinger equation. It has eigenvalues and eigenvectors. So, and if you solve this, say with some either iterative or with a complete solver, you will find these eigenenergies epsilon. Okay? So if you plot then these eigenenergies epsilon, you have one eigenvalue, another one, from bottom to top, you might have something like this. And if you have n electrons, you will need n such eigenvalues and eigenfunctions. So what one is doing is one is filling up the lowest n levels, just here, if the system is non-magnetic in the way which I've shown here. One does not even need to calculate, one can calculate if one wants more of these empty states here, of the empty eigen vectors of your Hamiltonian, but it's not necessary to calculate them. You must calculate at least as many as you have electrons. Or, I mean, always a factor of 2 for spin, if your system, depending if your system is magnetic or if it is not magnetic. So in practice, what one is doing is one has a Hamiltonian. That Hamiltonian is well defined once you know a density and once you know have an approximation for exchange and correlation. One calculates in one way or the other, we will talk about it in a minute, eigenvalues of this, and one takes the lowest eigenvalues and takes as the Kohn-Sham orbitals those functions which correspond to these low-lying eigenvectors. Okay, so this, it seems to be very straightforward and very easy, but there is one problem in this. And the problem is that this Hamiltonian here itself, it depends on the charge density. You can see it very clearly, for example, the Hartree potential here, in order to calculate, you need to know what is the density. But the density, you obtain it from the Kohn-Sham orbitals, so from the solution of this Schrödinger equation. So the problem which arises here is that you have an equation. In order to write down the equation, you need to know already its solution. You need to know the Kohn-Sham orbitals in order to be able to write the equation which the Kohn-Sham orbitals have to satisfy. So you see, it's kind of a circular problem, and this is known as the consistency or the self-consistency problem. We must be able somehow to find Kohn-Sham orbitals, which are eigenfunctions of an operator, where inside the operator, the operators in here are defined by n, and n, as you remember from the previous slide, for n, we need to know what are the Kohn-Sham orbitals. Okay, so this self-consistency problem, there are various ways how one can try to address this. And the way which is implemented in the PWSEF code and also in many other codes is to do this in an iterative way. Let me show so kind of the picture how one can imagine this iterative way. So this is known as a self-consistency circle. And the idea is, in the beginning, obviously, you do not know yet anything. Okay, so in the beginning, you have to guess somehow what the density might look like. And you can guess whatever you want. You can start with a guess, say, put as a density simply random numbers. Or you can put, which is most of the time done, you can put as a guess in the beginning a density which would just be the superposition of unperturbed atoms which do not interact. The only thing is that your starting density, it must satisfy, obviously, these two rules. It must be non-negative, and its integral must be correspond to the number of electrons you have in your system. Okay, so you guess anything, and you call this density which you have guessed the density at iteration 0. Okay, so now you have a density. It is certainly a wrong density, but it's an admissible density from the mathematical point of view. And with this density, you can now build this Hamiltonian from the previous slide. So you can go here. Now, having some density, you can write what is the Hartree potential, what is the exchange correlation potential. So now you can define this Kohn-Sham Hamiltonian. Obviously, it will be as wrong as the density will be wrong. This Kohn-Sham Hamiltonian will probably not be the one which we will have in the end. But you now have a Hamiltonian at iteration number I, in this case, in the beginning, at the 0th iteration. Now, with this Hamiltonian, you can now solve this Schrödinger-like equation, which I've shown you. So you have H times psi is epsilon psi, and you obtain, I have written here out, the output of this Schrödinger-like equation. You get energies and orbitals. Now you can take these output orbitals, take the square moduli of these orbitals. This gives you a new density, the output density. So you started with a guessed density to the left, and you end up with an output density of your system, which is of these new eigenfunctions of your Hamiltonian. And now you look at it. If you're in the first iteration, for sure, this output density here will be different from what you have guessed in the beginning. So you're comparing them. Are they more or less the same? And there is some criterion, some convergence criterion. In the beginning, certainly the answer is no, they are not nearly the same. And you go to the next step. So what you're doing now is you're taking these two densities, the one which you have guessed before, and the output density which you have just calculated, and you're mixing them together. In the easiest way, in the easiest case, you're just mixing as I've written here. You take a parameter alpha, which is a number between 0 and 1. You are taking a bit of the old density and the other bit of the new density. You're mixing them together. Now, this mixing is important in order to have this repetitive circle to be able to converge. If you do not mix and just take the output and put it as a new input, it's very likely that you will have oscillations going on forever. So this mixing is necessary for assuring convergence and for you can see it as if you were adding some kind of friction into your system. Okay, so you now obtain a new density. I call them I+1 of iteration I+1. This new density is now different from the one we have guessed in the very beginning. Now you set the variable I to the next one. So you have the next iteration, you use it again to build a Kohn-Sham Hamiltonian. You solve the Schrödinger equation. You get again a new density. And again, you are comparing, is what I plugged in more or less the same as what I get here? And you iterate this as a function of how your system is. You might need 5 iterations, you might need 10, sometimes one needs 200 iterations, it depends. And obviously there are many parameters in PW input files which you can tune to try to get better convergence on this side. But the basic idea here is always this here. You start with some guess, you build the Hamiltonian, you solve the Kohn-Sham equation, get new density, and you do this with the mixing. And finally, the so-called self-consistency is reached if the density you use to build your Hamiltonian is the same as the one which comes out of the eigenfunction of that same Hamiltonian. In this case, you are done and you have found the ground state density of your system. Okay? So this is in theory, in 2-3 pictures, how the self-consistent circle looks like. In practice, since this is a hands-on school, you will all see it starting from later this morning. This is a part of an output of Quantum ESPRESSO. And what you see here in the output is, it says in the very beginning, my initial potential, so the initial Hamiltonian, is guessed from a superposition of 3 atoms in this case. Okay, so here it takes atoms, and this is just taken as initial guess. As I've said, it could even be random numbers, but here the code has used as an initial guess a superposition of 3 atoms. It also needs to start with some guess for these Kohn-Sham orbitals. And here it takes atomic orbitals, but it is randomizing. So it's adding a little bit of random numbers to them to break some spurious symmetries which might be there. So this is what the code is doing in the beginning. It is guessing how the solutions might look like. And then it starts iterating, as I just said. It says iteration 1. It gets a guess for the energy, which certainly is very bad. And it says, but I see that the accuracy here in this case it's still very poor. It does the next iteration, has a better guess for the energy, and you see that the estimated accuracy is going down. there's a third iteration, and so on, and it will continue. In this case, you see until iteration 10 and iteration 11. And then you see here after iteration 11, obviously, this accuracy, you see it has been going down from 1.9 in the first step. This is, if you want, the comparison between the two densities, up to here already 10 to the minus 8 or something like this. And then at a certain point, it reaches its convergence threshold. Here, this is after iteration 11. And in this case now, the code prints out of this self-consistent Hamiltonian, which are the eigenvalues. So the eigenvalues, remember these lines where you put two electrons starting from the bottom. These here are the eigenenergies in electron volts of your Hamiltonian in increasing order. And it also tells you, okay, so in this case, the highest occupied level is minus 6.2. So this here is the highest occupied level. And the first level, which I did not occupy anymore, is minus 1. So you see here, and it has, in this case here, if you want, a band gap of about 5 electron volts. Okay? So this is what the code does. Then it gives you the total energy at this one. And you see now this accuracy, this conversion threshold, it's really very small now. And this is why it is said, okay, we have converged. In this case, it needed 11 iterations. So this is the basic thing. Whenever you run PW, so the basic DFT code of Quantum ESPRESSO, you will always notice this. It starts with some guess. It does a series of iterations. Hopefully, at a certain point, it converges. When it is converged, it gives you the eigenvalues of the Hamiltonian and the energy. Unfortunately, I have, when I was copying this picture here into my presentation, I was by mistake cutting here the left, because once it is converged, it is putting, the code is putting an exclamation mark in front of the converged total energy. So you can, if you use a grep of an exclamation mark in the output, you directly find the converged total energy. So unfortunately, I have cut this away without wanting. Okay. So this is what I've said. Now, as we know how in principle a ground state DFT calculation can be done, we have to ask ourselves, well, how is this done in practice? Because we have densities, we have Kohn-Sham orbitals, they are all functions of R, of space, and this must be stored in a computer somehow. A computer cannot store a function. A computer can only store numbers, a set of numbers. So any electronic structure code, not only quantum mechanics, any code will need a basis set. A basis set essentially is a set of functions. Here I call the functions B alpha, a set of functions, and whatever you are interested in, being the density, being a Kohn-Sham orbital or whatever, is expressed as a linear combination of some given basis functions. Okay? And which function you use as basis functions, this is kind of determining also which code you are using, because typically you cannot within one code change. Okay? So there are various functions which you can use to express your density and your orbitals as linear combinations. And so here again, I say this. So the function which you need to represent in the computer is this f. You have given, before you start your calculations, a set of basis functions. We'll talk about them in a minute, what they are. What the computer really stores is only these expansion coefficients. Okay. So for every function it needs to represent, it is storing the expansion coefficient for every basis function it has. This is in the computer's memory. Now, how many basis functions are there? I called here this number m, and this is the size of the basis set. And you can already imagine that if you have a basis set which is larger, then you will need much more memory in your computer, because for every function you need to store these m expansion coefficients. So on one hand, you would like m to be as small as possible in order to save memory. But on the other hand, you also want your basis set as complete as possible in order to be able to describe any shape of your function as a linear combination of your basis set. So many various basis sets can be chosen. Very popular are, for example, basis sets which are localized around given atoms. Or, for example, Gaussian functions which are centered on your atom, or atomic orbitals which are also centered on the atoms. But none of this is done in Quantum ESPRESSO. One of the defining features of Quantum ESPRESSO is that we are using plane waves as basis sets. So these functions V alpha, which are used in the Quantum ESPRESSO codes, are plane waves. What do you mean with plane waves? Well, here you see it explicitly. A plane wave is essentially e to the I, a wave vector times r. You can, so essentially, in other words, a plane wave is a sine and a cosine function, okay, with a given well-defined wave vector. And once you have defined the wave vector, you know what this plane wave is, okay? So in Quantum ESPRESSO, everything, densities, Kohn-Sham orbitals, and what you have is expressed as linear combinations of sine and cosine functions. And this has obviously important consequences. So why are we using these plane waves and not something which is localized on your atoms? Well, because the plane waves have a lot of advantages. So one thing is obviously they are very easy functions. So everyone can very easily integrate or take a derivative of a plane wave. So there are many, many expressions which appear in your equations are very easy to perform. The other thing is, if you have two plane waves with two different wave vectors, then automatically they are orthogonal, and two plane waves with the same wave vector, they are normalized. So plane wave is automatically an orthonormal basis set, which is also very useful in practice. The other advantage is that plane waves are unbiased in the sense that you have a system, you throw plane waves on it, and you do therefore not assume, all my electrons are close to the transition metals, or all my electrons are close to the center of my molecule. No, you do not assume anything. Every point in space is treated equally in the same way, and there is no bias in this. Another point is that since the plane waves are independent of where your atoms are sitting, you do not have a change of basis set whenever you move your atoms. So if you do some molecular dynamics or so, your atoms move, but your basis set remains the same. The basis set does not change with changing atoms, which is the case if you have, for example, atomic orbitals centered on your atoms. You move around an atom, you move the basis set, and therefore you have different basis sets for different geometries. And that means in practice that you have forces to calculate, so-called Poulet forces, and they are absent in codes which use plane wave. Another very big advantage is the convergence of the basis set size. This is something I will be talking about in the following slides a lot. So there is one number which you can increase or decrease, and with this number make your calculation or your basis set better or less good, and you can very easily in this way check on the convergence of your basis set. So it's really useful to have just one number which you change. And the other point is that obviously plane waves in sine and cosine, they are ideal for using Fourier transforms and going back and forth and solving Poisson equations, things like that. Obviously, I mean, the big disadvantage is that since plane waves have no built-in knowledge about what chemistry looks like, what an atomic function looks normally like, typically these basis sets are much, much bigger. So this number m, the basis size, is much larger than if you use atomic orbitals or if you use Gaussians or something like this. Okay. So now that we have established how we express our functions using kind of combinations of functions which look like what you see here, I have to talk about something which is intrinsic whenever you talk about plane waves, and this is periodicity. We will see in a minute later why it is so important that, or why periodicity of a system is so closely linked to the use of plane waves. But so for this reason, let me just say some more words. So imagine you know that a system is periodic. Here I just show it in 2 dimensions. So periodic means that you have a unit cell which is repeated indefinitely in all 3 dimensions. So here for showing this, it's just in a 2-dimensional world. So once you define your basic box, and the box does not need to be a rectangular box as I've shown here kind of a hexagonal box. So in this case, it's made out of 2 vectors. One of the 2 vectors of this box would be this one, the other this one. And this is the basic cell, which in a periodic system you imagine repeated indefinitely. Together with your basic repeating box, you define where the atoms are. So in this case, for example, I decide I put in every box 2 atoms, one at the origin. And you see, it's not even necessary that they lie directly, the atoms, inside the box which you define, which defines your periodicity. You can put them anywhere, but you will repeat the atoms as you will repeat the box. So now looking at this, probably it's not easy by the eye to see what kind of system you are calculating. You have this kind of box, these kind of 2 atoms. But if you, instead of plotting just 1 unit, plot now a 2 by 2 repetition of it, you see, okay, this already looks like here something which is cyclic, okay. And if instead of 2, I plot 3, you can see that we are coming closer and closer to the hexagonal graphene structure. And in fact, if you imagine that you would be having really an infinite repetition of this box with 2 atoms, you see that this gives you, in this case, a sheet of graphene. Obviously, I've chosen this example because in the exercises today, graphene will be one of the first exercises you will be capable. So periodic systems can either be, typically they are 3 dimensional. Here I've chosen a 2-dimensional system, but if you have a crystal, for example, you have a diamond or something like that, this is what happens typically with a 3-dimensional box with 3 lattice vectors, and you repeat it indefinitely. And inside this box, you have your atoms at well-defined positions. Okay, so imagine you have a system which is periodic, and you now would like to describe wave functions using plane waves in such a periodic setup. Now, one thing which you probably remember from mathematics, if you have a function which is periodic in real space, so you have anything, for example, a density which is the same in this box as it is in this box as in this box. So you have something which in real space is periodic. You calculate the Fourier transform, and you will find out that the Fourier components are nearly all 0, except for the Fourier components at very special discrete wave vectors G. And in fact, so in 1 dimension, where you can see it very easily, if your plane wave looks like e to the I gx, so just a 1-dimensional thing, you will have non-zero expansion coefficients only in front of those plane waves where this G vector satisfies the fact that it must be an integer number times 2 pi over L. So L in this case is in 1 dimension the size of the repeated unit. And this 2 pi over L, if you want, is the distance between non-zero Fourier components. Or in other ways, while originally you have had an infinite number of plane waves, now you still have an infinite number of basis functions, but now you have not a continuous, but you have discrete values of G, which you have to consider. This is thanks to the periodicity of your system. In 3 dimension, it's very similar. You have a 3-dimensional wave vector, and the wave vector of 3 dimension must be an integer multiple, m, n, and p are integers, an integer multiple of the 3 reciprocal lattice vectors. Okay, so also here you have now discrete plane waves rather than a continuous set of wave vectors in your basis set. In 1D, you can see it again here. So you have the possible non-zero G vectors are, well, obviously G equals 0. And then you have 1, 2, 3, 4, and so on, times the basic 2 pi over L, which is the distance here. And you can already see that the larger your unit cell, so if you double your unit cell, L becomes larger, and this distance between the discrete point becomes smaller. If you double the size of your unit cell, you will have double the density of G vectors in your basis set. Okay? Now, a wave vector is always linked, obviously, to a wavelength. And if you plot the wavelength, or if in the same thing you look at what is the wavelength of all these wave vectors here, so you have the wavelength here. You have lambda is equal to the size of your box, then the size divided by 2, 3, 4, and so on. Okay? So the wavelength which you are describing with a given plane wave is inversely proportional to the G vector. So now, thanks to the fact that we live in a periodic world, we now can say, okay, instead of having an infinite number of basis vectors because G is continuous, we now still have an infinite number, but now we have discrete values for G. Okay? And the values are these here. But still, in order to do a practical calculation, we need a finite number of basis functions. So somehow we need to take out of this infinity of possible plane waves, we need to take only some. And this is done by imposing, in fact, a minimal size of features you want to be able to describe in your system. Okay? So one is saying, okay, I know that my density or my orbitals, they will not vary on the scale of the atomic nucleus. They will vary on the scale of, I don't know, perhaps half or a tenth of an angstrom or something like this. So we define, and this is the one parameter which defines our basis set, we define a minimal wavelength which we want to be able to describe. And this I show you here. So this is again my G vectors, my discrete G vectors. And now I define a minimal wavelength lambda min. And you see here, for example, if I say lambda min is this value here, then L/4 is still a wavelength which is larger than the minimum you have imposed. But here then L divided by 5, 6, and so on. This is a smaller wavelength. And here the same is for the minus G's here. You have again the same thing. So imposing a minimal wavelength which you want to be able to describe kind of cuts out of this discrete but infinite number of possible plane waves, all those out which are lying to the left or to the right of your cutoff wavelength. Okay? So this is basically the idea in one dimension. You have one parameter which describes how good your basis set is, and this is obviously something system dependent, and it's this minimum wavelength lambda min. So for practical reasons, one is typically in an input file, not describing what is lambda min, but one is describing what is the maximal norm of the G vector which comes in. And in fact, so the maximal value of the G vector obviously is inversely proportional to this lambda min. So it's the same if you describe a minimum wavelength or a maximum norm of the G vector. And in fact, what really one puts into Quantum ESPRESSO in the code is a cutoff energy, which would correspond to the kinetic energy of that maximal G vector. So in a PW input file, you will put in ECUT. The ECUT defines via this equation a maximum norm of the G vectors and therefore a minimal feature size which in your system you would like to describe. So if you're not in one dimension but in 2 or 3 dimensions, it looks a little bit like this. The G vectors, as we said, are integers times the reciprocal lattice vector. So here, reciprocal lattice vector 1 would be in this direction, reciprocal lattice vector 2 would be this vector here. And then you have integer numbers times this. You have a discrete set of possible G vectors, which are compatible with a periodic system, a discrete set of G vectors, but an infinite number. Now you impose a maximum kinetic energy, or if you want a minimal feature size you would like to be able to describe. This defines you a norm, Gmax. Okay. This looks in 2 dimensions now like a circle. In 1 dimension, it was the 2 blue lines I've shown in the previous slide. In 2 dimensions, it's this circle. In 3 dimensions, it would be a sphere of this radius of Gmax, which is related to the kinetic to the cutoff energy. Okay, so you have this, and now you consider only those plane waves which have a norm which is inferior than your cutoff, and now you are left up with a basis set which is well defined because it is a finite number of G vectors, and these are they. Okay, so this is how in Quantum ESPRESSO you obtain a basis set. It is by imposing a minimal feature size or a cutoff energy which cuts the total number of possible G vectors to a finite number. Okay, so now I need to say something about orbitals and charge density. So what we have done now is we are saying, okay, we have a function which is periodic, for example, a Kohn-Sham orbital psi L. This Kohn-Sham orbital is written, as we have said, as a linear combination of these basis functions. The sum goes only over these allowed G vectors which lie inside our sphere. Okay, and what the computer stores for every plane wave is this expansion coefficient here. This is what is stored in the computer. So imagine we are doing this with a well-defined cutoff, with a well-defined Gmax for the Kohn-Sham orbitals. Then the next step, which we would need to do, is to calculate the charge density corresponding to those Kohn-Sham orbitals. Remember that the charge density is calculated by calculating the square modulus of the orbitals. Now, if you see this here, this is in real space a product of two functions. Fourier analysis tells you if you have in real space a product of two functions, this corresponds in reciprocal space to a convolution. So if I write this down here, what is the Fourier transform of the density? So this is now a function of G, okay? Then I obtain here again a sum over all possible vectors, because this here will also be periodic. So I have again a sum over G primes. And I have something like this, psi of G and psi of G minus G prime. Now I know that this term here, the psi tilde of G prime, will be non-zero only if G prime lies inside my sphere, because this is precisely how I've defined it. Okay? So we can restrict the sum over G prime to those lying inside the sphere. But now you see what happens. The vector G, in fact, it can have a norm which is larger than the maximum norm allowed for the wave functions, because even if, say, this G here has a norm 2 times the maximum G, then if G prime is G max, you still can have here a non-zero element. So Fourier analysis tells you that the density, because it is a product of two functions which are written with the cutoff G max, the density will have much higher cutoff. In fact, it will have Fourier components which are non-zero up to 2 times G max. Okay? So now this is very important, that in these calculations, you need 2 different basis sets. One basis set for the orbitals with a given cutoff energy, and one basis set for the density, which will contain many more G vectors, simply because you have 2 times G max here, and you therefore need for the density a cutoff which is at least 4 times the cutoff for the density. 4 times because G squared goes into the energy. Okay? So this is, in fact, the reason why you will have always 2 cutoffs. And if you do not do this, then you get so-called aliasing or aliasing errors in your Fourier analysis, and this is nothing which you would like to have in your code. Okay? So at this stage, we can say, okay, due to the properties of plane waves, the cutoff for the density must be 4 times the cutoff of the wave function. Later, towards the end of my talk, you will see that sometimes one needs even a higher cutoff for the density. Okay, so this is how it looks in PW. This is an absolutely minimal input file here, and the minimal input file tells you, okay, here I use for the wave function EKW of C a cutoff energy of 60. The code reads this. Oh, why does this continue? The code reads this, and in the output of the code it says, okay, my kinetic energy is 60 Rydbergs as written in the input. For the charge density, I will use 4 times like it. So obviously the code knows about these Fourier analysis features. Okay. So 64 times gives you this here in the output. Let me just say one thing which you might observe is, if you are changing the lattice constant of your periodic system, then sometimes you might observe something which is happening here. A strange discontinuity when you are increasing the lattice size of your system. So how can it be that one would expect that functions kind of behave in a continuous way, but sometimes you see discontinuous jumps of the energy? The reason for this is, as you increase the lattice constant of your system, you are making this grid of G vectors denser and denser. Remember that the distance between adjacent points is 2 pi divided by the size of your system. So increasing the lattice constant here to the left gets these dots closer and closer and closer. You keep a fixed cutoff energy, obviously, and then at discrete intervals, some points will fall within the sphere, and you have, in a non-continuous way, you will have a larger basis set. And the larger basis set, if you're not at convergence, means that, that the energy goes down. So these jumps, and they are obviously not very pleasant, especially if you are trying to do molecular dynamics, where with a variable cell, where the cell size can change. And this problem has obviously some solutions. I will not explain them in detail here, but if you're interested in this, look in the input descriptions for the variables EC fixed, QCAT-C, and Q2 sigma. You will have in the input file to set variables like this to take care of eventual jumps in the energy when you change the lattice constant of your system. This was just some comment I wanted to make here. Now, very important is something I have not mentioned yet, is the fact that even if your system is periodic, your orbitals typically are not periodic. In fact, we all have learned in solid state physics Bloch's theorem, okay, which tells us that, in fact, the Kohn-Sham orbitals in a periodic system, okay, they have a label, a K label, a wave vector label, and they have the shape of e to the ikr. So here you see again a plane wave with a wave vector k multiplied by a function u. And in fact, only this function u here is periodic. The psi's, you see, this here, k, is not necessarily one of these points on our grid. And the psi function itself is not periodic, only this part here. So what does this mean for what I've just been saying up to now? If u is a periodic function, then u we can express on this grid of g vectors I've just been saying before. So u we can express in our basis set with a discrete grid of g vectors, just like we have been saying so far. Now you put this u into the definition of a Bloch vector, and you obtain something like this. And now you see that you have again an expansion in the terms of discrete set of g vectors, but the effective g wave vector is no longer g, but is always k plus g for a Bloch orbital with the wave vector k. Okay, so you have this thing which is shifted by k. In other images, so this is the image we have seen before, is where we did not have any k point. Now, if instead of g you have k plus g, you can imagine that this is always shifted away from this grid from what it was before. The cutoff remains obviously the same. It's a sphere centered around 0. And the k vector for a given Bloch orbital, in fact, would be here this small vector here. This would be k. Another k vector would mean this. So a Bloch function for a wave vector k here has a basis set given by plane waves, which is given by these functions inside this circle. Okay? So for different k vectors, you will have a different three-dimensional grid of allowed g vectors. It is very clear that if you take if you add to any k vector a reciprocal lattice vector, then you are shifting this already periodic set of black points so far that you cannot distinguish it anymore. So this kind of explains again to you why, in fact, the system is periodic in k space, and one needs to consider, in fact, only what for k, what is happening inside the first Brillouin zone, because anything outside the k vector, outside the first Brillouin zone, corresponds by periodicity to a point inside the first Brillouin zone. So if you have your periodic system, you have to sum over all possible k vectors, but the k vectors are restricted to lie inside this first Brillouin zone. And this is done in Quantum ESPRESSO quite easily. If here again, I show you a picture of the Brillouin zone. So imagine this here is reciprocal lattice vector 1, reciprocal lattice vector 2. The Brillouin zone, in this case, if they are rectangular, it will look something like this. And in Quantum ESPRESSO, you give in the input file, you say, I want to sample the Brillouin zone, in this case, for example, with a 4 times 4 k-point grid, and then it would choose these k-points. And each one of these k-points corresponds to what we have seen here before, to this shift here of the k plus k. Okay. Now, very often it is not useful to take a grid in k-points like this, but one is shifting the k-point grid by half the distance between these k-points. So if I do this, this here would be the shifted 4x4 grid. So you see, I'm shifting the same grid, and I'm just shifting it by half the distance between all these points. Why is it useful to shift your k-point grid? Well, because of symmetry. You see, for example, so if you have a symmetric system where, for example, this wedge here of the Brillouin zone would be equivalent to the upper wedge here, then this point here has in the Brillouin zone 8 friends. So 1, 2, 3, 4, 5, 6. There are 8 points which are equivalent. So in order to calculate the charge density for these 8 points, you just need to calculate at one single point. If you have the much more symmetric non-shifted grid, you have no single k point which corresponds to 8 other points. You can see this both in the non-shifted grid, you always have the k equals 0 point. And whatever is the symmetry of your system, the 0 point here, it will always end up on itself again. So here symmetry is really a handicap, and shifting the k points, in fact, leads to grids with the same amount of calculations, give you a much faster convergence. So in a PW input file, this Brillouin zone sampling is done just by saying, okay, I want k points, I want an automatic grid. And in this case, for example, you can say, okay, I want in the x and y direction 9 points, in the z direction only 1. This might be, for example, if you have a 2-dimensional system like graphene. And then the next 3 numbers is always 0 or 1. It tells you for x, y, and z if the grid is shifted or not. So the 9, 9, 1, 1, 1, 0 selection would be a 9 times 9 grid in 2 dimensions, which is shifted, and a non-shifted single point, typically the kc equals 0 point, in the 3rd dimension. And in the output of Quantum ESPRESSO, where it gives you the k points it's using, it gives you, okay, this here leads now in this case to 25 non-equivalent k points. And you see every k point, these k points have different weights. This is what I've said here. For example, here, these points which have a multiplicity of 8, one will calculate them only once, but give them a higher weight. And you see here, there are some points which have a high weight of 0.09. Other k points have a much lower weight, like here, like the last one, which is 0.02. And you also know that all these k points have as a 3rd component 0, because we have only one k point, 1 point in the z direction and do not shift it. So this is always 0, therefore. Okay. So this is how plane waves, your basis set and so on, is linked to also to k points and to this. Okay. So now what happens if you have a system which is not periodic? Well, in this case, one is introducing a supercell. With the supercell, in fact, one is, I show you here, one is simply taking a cell which again is repeated periodically. This is also of today's exercises where you will calculate benzene. So one is putting your non-periodic system size and isolate molecule in a cell which is so large that the distance to the neighbors in one direction or in the other direction and also in the 3rd direction is so long that you effectively cut off any overlaps of wave functions and so on. Okay? So a supercell essentially in these cases means that you're taking as large as you can afford computational cell in order to ensure no interaction between these images. Now, this is not always so easily possible, because if your object is charged, for example, if this molecule was charged, then you can use as large as you want a unit cell. The Coulomb interaction will always be there. The same if you have a molecule with a dipole or something with a dipole, it will interact with the dipolar interaction. You cannot have a cell which is so large that, that this interaction goes completely away. Now, this issue, so for charged or dipole system, has 2 solutions. If you have a 0D, so say a molecule or a cluster, something which really is not periodic in no direction, then you can use the input variable assume isolated, which essentially in one way or the other cuts off Coulomb interactions beneath the length which are intramolecular. So the Coulomb interaction will be cut such that essentially one molecule cannot see the other, and therefore you are getting rid of this wrong periodicity which you might not want. So this is possible if you have 0D, so no periodicity at all. Things are more complicated if you have, say, something like a graphene layer or a surface. So these are systems which are periodic in 2 dimensions, but which are not periodic in the 3rd dimension. In this case, one is also using supercells, which have a lot of vacuum in the direction where the system is not periodic. But still, if your surface is charged, or if you have dipoles along the surface, then one surface will see the other. And in this case, in this case, you will have to be very careful, and there again, look at the input description for the very deep field. You will have to put in something into the vacuum to effectively decouple one surface, one image from the next. So in Quantum ESPRESSO, you can calculate also non-periodic system, but always with these periodic codes, but you have to be careful in many cases. So I would like to use the last minutes which I have to say something about the other big issue, which are pseudopotentials. So why do we need pseudopotentials, or what are pseudopotentials? So you remember in my very first slides where I've shown the Kohn-Sham potential, there was the so-called external potential. And the external potential, as I've said, is the potential due to the nuclei. So it is a very easy shape. It is simply minus 1 over the distance from this nucleus times the nuclear charge, because it's simply a positive charge pointwise, which is attracting all the electrons. So that would be the pure Coulomb potential. Now, why are we not using the pure Coulomb potential? Well, the answer is, look at this here. If you're here on the left side of my graph, you have the nucleus, and this here is the radial part of some atomic wave function. This might be, I don't know, 4s or so, I don't know, I have to count the nodes here, wave function of your system. Then you see that close to the nucleus, this function, in fact, because say the 4s needs to be orthogonal to the 3s, needs to be orthogonal to the 2s, which needs to be orthogonal to the 1s. Okay, so because of orthogonality, these radial functions, they have very fast oscillations, but these oscillations are in a region of distance from the nucleus where anyway no chemistry is taking place, where no bonds with their neighbors are happening. The bonds with the neighboring atoms will probably happen in this region where you see your radial wave function is perfectly smooth. So this is a problem for us, because as I've been explaining in length before, when we use plane wave basis sets, we define a minimal wavelength lambda min up to which we can describe features. So if we want to describe features which are as fine as what you see here in this radial wave function, you need a very small lambda min, and at the same time, therefore, a very high kinetic energy cutoff. And this is something which you really do not want, because the calculation would become extremely expensive and in most interesting systems undoable. And you would have to pay this high price for something you're not interested in, because the shape of this wave function close to its nucleus is for most applications entirely irrelevant. So the idea of a pseudopotential is the following: is we try to replace the Coulomb potential, the 1 over r potential due to the nucleus, by something else, which has as a solution a radial function, which looks here exactly like the right atomic all-electron wave function for distances further than some cutoff distance. Okay? And inside this cutoff sphere around the nucleus, where anyway no bonding is supposed to happening, no chemistry is supposed to happening, you would like the function to be perfectly smooth and go smoothly to 0. So it's clear that obviously this blue function here would need a much lower kinetic energy cutoff, a much higher lambda min would be enough to describe this function with respect to this, the red function here. So a lot of kind of research has been happened how one can create effectively such functions. And the most important lesson which people have learned is that this can only work if you have norm conservation. Norm conservation means that the integral inside this cutoff sphere around your atom, the integral of the norm of the all-electron wave function must be the same as the integral of the blue pseudo wave function. This must be the case. Otherwise, your atom will have wrong scattering properties and things will not work. So one thing which people have learned, they must construct the blue line in such a way that there is norm conservation. But apart from this can perfectly well be done. And I show you here how such a pseudopotential can look like. Here, this is for molybdenum, a pseudopotential. What you see here is the dashed line. This is the simple external Coulomb potential, which we would have without pseudopotential. So it's the function which goes to -infinity, -1/r, you see here. The pseudopotential, you see, has, compared to this easy form, some very weird forms. You see here, far from the atom, it is the 1/r of the exact one. But then as you come closer within this radius, the shape is quite strange. And you see also that it is angular momentum dependent, which potential. So the pseudopotential is a potential which electrons of various angular momenta see, and it has this shape. Far away from the atom, it is the same as the Coulomb potential. Close to the atom, it has an L-dependent shape. And how is this obtained? Well, essentially, one calculates DFT for an atom, and one is inverting the Schrödinger equation to find out which potential do I need to put in order to have as a solution the blue line instead of the red line. Okay, so this is how a pseudopotential looks like. And in Quantum ESPRESSO, when you run it, the pseudopotentials, you have to provide them as a user in the form of files. Okay? These are files, and these files contain numbers on a radial grid and tell you precisely the shape of these functions here, the solid lines on a radial grid. For every element, a different one. Okay, so here, for example, this is an example for some system which I've been calculating. It has 5 different elements. In the input line, one says for every element, well, what is the mass of the element? And then one says, which is the name of the file which you want to use for this. And if you look at these file names, you can already see that since the pseudopotentials have to be calculated by inverting a Schrödinger equation of a DFT calculation on an atom, you need DFT to calculate a pseudopotential. So therefore, the pseudopotentials depend on the functional. And so in a normal PW calculation, or in a normal Quantum ESPRESSO calculation, you will not need to put into your input which functional you want to use, because the code automatically looks, I have this pseudopotential, so I need to use the functional used for this one. In this case was the PBE functional. Okay. So now as a user, you must be careful that if you have various elements in your system, like here, you must use only pseudopotentials which are all been created with the same functional. Otherwise, the system on your composite system, it would not know the code which functional to use. Here, the density functional it will be using is obviously PBE. Okay? So be very careful and know what you are doing. If in the input file you say, I want to use, I don't know, the HSE functional, but I have pseudopotentials which come from a different function. You can force the code to do this. If you do not force it, it will not like to do this and it will complain. So you should know what to do, and keep in mind that pseudopotentials which you are using are functional dependent and so on. Okay, so this is the basic idea of pseudopotentials, and I would like to finish what I have to say by pointing to 2 different classes of pseudopotentials which are very important these days, which are so-called Ultrasoft pseudopotentials and pore pseudopotentials. Now, this is something which goes beyond what I've just said, what norm conservation is. Remember, norm conservation means that in close to the atom, the integral of the square of the all-electron wave function must be the same as the square of the pseudo wave function. Now, however, in many elements, this is a serious problem. For example, look here, this is oxygen. Okay, and oxygen here, the all-electron wave function looks like this. And there is not much wiggles or something you can get rid of. You will have your pseudo wave function, if you use a norm-conserving pseudopotential, will have to describe this this peak here of the 2p wave function of oxygen, and it will require a rather high cutoff, which one would like to avoid. Same problem appears if you have, for example, 3D transition metal or 4F rare earth elements in your system, where you have no wiggles and nodes of your wave function which allow you an efficient serialization, like in the picture before, but where still you have something which is very localized, and you would like to get rid of this very small wavelength which you need here. So this norm conservation constraint is a problem in many kinds of systems. And the way to go beyond this has been invented by David Vanderbilt now many years ago. And essentially, in these Vanderbilt ultrasoft pseudopotentials, the idea is to release this need of norm conservation, which I've mentioned before. Okay, so a norm conserving pseudopotential would require you to have a pseudo wave function which more or less follows the all electron wave function with these very steep features here. What Vanderbilt has allowed is that your pseudo wave function looks like the dashed line here, so much smoother. In this case, this is again oxygen 2p, much smoother than this one here. But it's also clear that this here has a different norm inside the radius than this function here. So he had to get rid of norm conservation to do this. Now, how can he do it that without norm conservation, he still gets excellent results for his pseudopotentials? Well, the price which one has to pay here is that one gets a more complicated expression for the charge density. Okay? So far, what we've always said is that the charge density is the sum over the square moduli of your Kohn-Sham orbitals. However, if you have Ultrasoft, and the same story is true for pore pseudopotentials, which are for many users' points of view exactly the same thing. So in Ultrasoft or pore pseudopotentials, the density is defined as it was before, but then there is also an additional term here, which is called the augmentation charge density, which is always localized close to the atoms, to those atoms which have an ultrasoft pseudopotentials, and which needs a very high cutoff, because this augmentation charge here will have to account for the difference between the square modulus of the dashed line and of the real line. Okay? So one obtains, I will not give you here the expression because it contains a lot of projectors. It's not something easy to or pleasant to look at, the expression for the augmentation charge. Just keep in mind that whenever you have a pseudopotential in your system, which is ultrasoft or norm conserving, the code will add something to your charge density. And as the code adds something which will be very localized to your charge density, this means that the 4 times cutoff which you use for norm-conserving pseudopotential will not be enough. You will need a much higher cutoff than this. So if I go back to this input, which I've shown you before, here in this system, okay, there are 5 elements. And if you look at the file names of these pseudopotentials, well, we have already discussed, it says you PBE. But the file name here also in all cases has this US. Whenever you see US in the file name, and you can also look inside the file where it's written explicitly, these are US pseudopotentials. So beware that you need to have higher cutoff than 4 times the wave function cutoff. And this is where it comes from. It comes from augmentation charges, which have to account for the difference here close to every atom. But this thing works very well. So here, for example, this is from this old Vanderbilt paper. Here's shown here as a function of the cutoff energy, how the energy converges. And you see if you have a norm conserving, but then conversion is very, very slow, and you need to have very high cutoffs. With these ultrasoft pseudopotentials, already here in this case, a 30-40 Rydberg, you have perfectly converged total energies for the wave function. So these pseudopotentials, either pore or ultrasoft pseudopotentials, allow you to get away with a rather low cutoff for the wave functions, but beware, the density will still need the high cutoff. Okay, this I've written here again explicitly. You need more than 4 times the cutoff for the orbitals. And here, really, I have so many years of experience with new students and people doing Quantum ESPRESSO. I can tell you the most, the beginner's mistake I've seen most in all those years is that people do not realize that some pseudopotential is ultrasoft or pore and do not specify the second cutoff. So in a typical input file, which you see here on the right, EKWFC 40, this is for the Kohn-Sham orbitals, the cutoff. If you have also some of these pseudopotentials shown to the left, you have to define another cutoff for the density. See, it is more in this times, more than 4 times 40. a typical thing is either 8 or 10 is a typical factor. So if you want a rule of thumb, but in truth is you must check convergence not with 1 cutoff, but with 2 cutoffs in your system. Okay. So with these words about the most common beginner's mistake, all that remains to me is to wish you happy computing in these in the tutorials, which will start now. And if some of you have questions, I'm obviously very happy to answer questions.
Thank you, Ralph. I don't know how the local organizers thought we should proceed. I would gladly fade into the background.
There are 4 questions on the chat. I don't know, Ralph, if you can read through them.
Wait, I can, because I'm having full screen of my presentation. Let me see. Besides, I just by chance now see that it's 10:000, so this is a perfectly timed talk. Huh? But I cannot see. Why can I not see the question?
Yeah, the first one.
Ivan, why don't you read?
Can you read it to me, because I cannot see it here now?
Yeah, so one is what are the pro and cons, or the pro and constraint of that 0.5 shifting? I believe this is about the
the K point,
yes,
K
exactly,
point grid
yeah.
in the Brilliant zone. So
yeah,
so
then sorry, there is another one saying the same question. What do I need to shift the K mesh?
Okay, so yeah, let me say something more about the K point. Can you still see my screen?
Yes,
here?
we can. Yes.
Okay, good. So this is very much related to symmetries of K points. Obviously, the code tries to calculate as little as somehow possible, and it is employing the symmetries of your system to reduce the number of K points. Okay, so if you have, like you have here, for example, a 4 by 4 grid, okay, then some of these K points are equivalent, okay, due to your symmetry. So for example, you might imagine that you can here have a symmetry for the plus minus x plus minus y, and concentrate only on the irreducible wedge of this rectangle here. Okay, then the code would automatically calculate only one of the various equivalent K points, and give that K point a higher weight. Okay? Now, if you have a shift of your regular mesh, then typically the points lie on less symmetric points in the Brilliant zone, meaning that the symmetries allow you a higher multiplicity of your points. So it is all due to, in fact, due to symmetry. So the big advantages is you have, with less calculations, you have more sampled points because the K points lie on less symmetric points. You can see this, I mean, as I said before, the key thing of a not shifted mesh is that the K equals 0 is always in the non-shifted mesh. And the K equals 0, whatever is the symmetry you're doing, lands on itself. So that point counts only for itself. If you shift it a little bit to a point which is not symmetric, lying out of the center, then every symmetry will bring this point on a different point, and therefore you obtain effectively more K points with the same calculation. So the advantage of shifting is that you have a faster convergence of your K point sampling if your grid is shifted. The disadvantage, and there are disadvantages, is that sometimes you want to compare a calculation with K points with a different calculation with less K points, but a larger unit cell. Okay? So you can, for example, take a supercell where you double the dimension of your primitive cell in all directions. And then in order to have an equivalent calculation, you should have exactly half the number of K points. Okay? And this equivalence of a supercell with a shifted mesh goes away. Because for this equivalence, you always need, again, the K equals 0 point and the regular mesh in your system. But these are really very special cases where you need, for some reasons, to compare either a supercell with a K point calculation cell, or it can happen that if you want to calculate some electron phonon properties, you need a particular regular mesh where it cannot be shifted. So in special applications, it can happen that shifting is not good. If your goal is really only in a periodic system to converge as fast as possible with as few k-points as possible, you should always shift. Other questions?
Yeah, there are some others. So how far can we set the distance between supercell in case of not periodic system to neglect the interactions?
So there are no rules of thumb. Some people say, 7 angstrom is always enough. Some other people will say in 7 angstrom, it's clearly too close and it must always be 11 or so. This is something where you typically have to do a convergence test. So you calculate it with say 8, 9, 10 angstrom difference between your copies. And then you see, it depends very much on the system, as I've said. If there are dipoles, if the system is somehow charged, then you will need much more vacuum than in cases where everything is neutral.
Very good. I understood that it often gives much faster convergence, as there will be more equivalent k-points. Is this right? Maybe this is a question related
Yeah,
to
exactly. This is what I just said. It converges faster.
Yeah, another one is cutoff always 10 times. If we increase 100 times, then is it effective?
It's certainly not effective, because if you have 100 times, so I mean, you probably think about the ratio between the cutoff for density and wave function, I imagine. And so at a certain point, using a higher cutoff for the density will make a calculation heavier, but you will be at convergence. So a typical thing, nearly always you get away with the effect of 8 between the density and the wave function cutoffs. In fact, the people in Lausanne with Nicola Mazzari, they've made a very thorough testing of cutoffs for all kinds of pseudopotentials. And with the pseudopotentials, they recommend in their database, these they get for all elements except iron, they get optimal results with a factor of 8 between the two cutoffs. Only iron, they needed 10. But that is specific to those pseudopotentials they recommend.
Okay, there is the latest question from the Zoom, and then we switch. There are a few questions from the streaming as well. So the latest from the Zoom is, beside of the Eiger cutoff for the density, is there any disadvantage to use the Ultrasoft pseudos?
The disadvantage, it depends. One, for me personally, the biggest disadvantage of Ultrasoft pseudopotential is that some advanced features might not be implemented. For example, I recently was interested in some electron-phonon interaction, some systems, and that was not yet implemented for Bohr or Ultrasoft. But generally today, nearly always people use Bohr or Ultrasoft pseudopotential, simply because one can get away with much less computational effort.
Okay.
And let me just say, so
yes.
the issue arises mainly if one uses hybrid functions where one needs to calculate exact exchange. That is still an issue where I think we should all work more on implementing that with Ultrasoft pseudopotentials in a better and even faster way than it is now.
Okay, there are a few questions from the streaming. So even with periodicity, what is the reason of band bending as we go to higher dimension supercells?
What does this mean, band bending? I don't understand this question. So typically when you have an interface between two different kinds of materials, you have a band bending, yes, but I don't see how this is linked to periodicity in higher dimensions.
Okay, let's go to the other one.
I'm sorry.
How to create an ion in Quantum ESPRESSO so that the ion absorption on the surface can be studied?
So no, what you can do is you can create an ionic system by telling in the input file that you want to have a charged system. So you can say, I want to have one or two, 3 electrons more or less than it's neutral. So your system will therefore be charged. Then it is quantum mechanics which decides where the system prefers to take away the electron. If you have, for example, an atom on top of a surface and you take away an electron, that this electron will prefer going away from the atom or from the surface. This is quantum mechanics which decides where it goes away. This is not something which you as a user can and should change. Okay, so you can in the input file simply say, I want more or less electrons in my system, but where in space these electrons decide to localize, this is physics which decides.
Which pseudopotential is recommended for computational expensive phonon calculation? Maybe this is something is going to be answered during the school, I think.
Yeah, I think it will be seen during the school. Let me just say for pseudopotentials, I recently like very much this pseudopotential table, which has been tested. I just said it before in Lausanne. It's the SSSP pseudopotentials. So if you type in Google SSSP pseudopotentials, you find a table, a periodic table. It has only for the functions PBE and PBE sol, but it gives you recommended cutoffs, everything, and they are very thoroughly tested. And I mean, there are many other libraries for pseudopotentials. Recently, I've made good experience with those.
Okay, the last from the online, is there a way to predict how many K points will an output file process given a certain mesh? For example, how many K points will a 6 × 6 × 1 mesh have? Please assume no symmetry.
It depends on the symmetry of your system. So in principle, if you're 6 × 6 × 6, it's the number of K points is that you multiply that. But then, luckily, the code finds out that.
Sorry, I have the question and with please assume no symmetry.
If you assume no symmetry, then if you have a 3 × 3 × 3 grid, you will have 27 K points. But
okay, there are a few big questions from the Zoom. The last two big. I don't know if you can read them yourself because it's quite long, or otherwise I go through it. So one is, as one can understand, a large number of failure can come from incorrect use of pseudopotential, grid choice resolution, etc. In this regard, it will be great if everyone who use Quantum ESPRESSO took this as a rule at the end of their scientific work, say at the stage of making an article available on the internet, to place their input script to an open library. What do you think? Maybe this is in progress.
So this is a very big topic, not only for pseudopotential. This goes into these big discussions which are taking place these days about open science. Okay, so in principle, the good thing, the good practice should be for everyone, and especially for those who enter the field now. When you publish something, it should be done in such a way that anyone can repeat your calculations. Okay, so that is in principle the goal which one should have. Science should be reproducible, and you should have either on some GitHub or some other repository, some way where people find all the data they need, not only pseudopotentials, but as you say, also input files and so on, to reproduce the calculations. So this is where the world is going, I think, and where it should be going, and editors should insist more on this is being done. Having said this, many people do not want to do it, because if you give away your input files, everyone can do your calculations, and people, for the wrong reasons, I think, they want to keep the thing, only I know how to calculate a graphene sheet, and I do not want that others also can do it easily. And so some people, especially, so some people are picky about giving away input files, which I think is the wrong attitude.
Okay, so I suggest that there is only one last question from the streaming, and then the Zoom, maybe we reply here in chat. I mean, we are always able to reply here, and then Ralph will be available also in some breakout room, I believe, at some point during the school. So the last one I take from the streaming is possible to change the electronic configuration of the pseudopotential of the atoms for droplet system? Well,
so first I should say the idea of pseudopotentials is that they should be transferable. Meaning that if you have a pseudopotential, say, for carbon, then you should be able to use this very same pseudopotential. If you're in graphene, if you're in diamond, if you're at high pressure, if you have an atom, in whatever chemical environment this carbon atom is, you should be able to use the same pseudopotentials. They are made for this. Okay? So this is point number one, transferability. However, if you think you are in such a special case that you need, because I don't know, the electronic environment is so strange, you need to construct new pseudopotentials starting from different electronic calculations. You are free to do so. And as I said in the beginning, there is the atomic code distributed with Quantum ESPRESSO, in which you define the electronic configuration of the atoms upon which you construct your pseudopotential. You can do it, but especially for beginners, I do not at all recommend starting to create your own pseudopotentials. This is a source of the most serious kind of errors which can appear. There are very good pseudopotentials ready for download everywhere.
Okay, I think we can close it here for now. Take a break of 10 minutes before 15 minutes before we have the hands-on session. So thank you very much, Ralph.
Okay, thank you very much
for this great talk. And
let me just say, if there are more questions which and you want answer, you can write them on Slack. So we can read them, because I see there are other questions going in the chat. If you write them on Slack, we can answer. We can answer there.
Okay.
Okay, we'll reconvene in 15 minutes for the lab session. See you soon. Okay, shall we start? Is Pietro connected?
Okay, let me share the screen.
Shall we start?
Yes, yes.
Okay, cool.
Just let me share the screen, please.
Before we start, Petros, if you give me 1 minute.
Yes, yes.
Wanted just to share a few info with the participants here on Zoom.
Okay, okay.
So, I mean, we've been repeating many times in this. In this introductory lecture, we are doing also, we are experimenting, let's say, this formula ourselves as well here at the ICTP. So we have seen that there are a lot of people following in streaming, and since they cannot interact, we will favor their question during the lecture. Okay. So, but you have an advantage here, and the advantage is that you have the Slack channels. So we encourage everybody that is attending and is selected to participate in the Zoom meeting to please use the Slack channel for any question. I mean, starting from now during the lab where we expect to have the majority of the problems, but also during the lectures, if you use Slack, we have much more people there that are following the channels and that can reply to your questions. Okay, so if we want to try from now on that the people that are attending here in Zoom write their question on the Slack channel. So let's see how it works, and then we try to figure. Okay, Pietro, your stage is yours.
Okay. Okay, can you okay, yeah. So greetings to everybody, and sorry. Okay, greetings to everybody, and welcome to this first hands-on session of the there is this annoying green line. Okay, never mind. Okay, greetings to everybody, and welcome to this hands-on session. This first hands-on session. It will be the first one, so it will be mostly a warm-up for the next days. So we are trying to see how things works. I am Pietro De Rugas from CISA, and I will be presenting this hands-on. And other persons that will be tutoring you will be Anton Kokal, Shanmei Duan, Matic Pobernitz, Umesh Mondal, Matej Jusz, and Yanin Kui. There will be the other tutors that will be available in the breakout rooms whenever you have issues and problems with any one of the exercises. Okay, the topic of the exercises of today are, the first example will be the compilation of Quantum ESPRESSO as the first example to show you how to compile the program. And then we will show you how to run some basic calculation using pw.x, that is the program that Ralph has just presented during the lecture of this morning. And then we will show how to use post-processing, the post-processing tools for plotting the molecular orbital density, charge densities with pp.x, how to compute density of states and plot it with dos.x, and then how to compute the band structure and plot it with And okay, this is about the documentation of Quantum ESPRESSO and how you can, where you can download it. Ralph has already said many of these things during the lecture of before, so I will skip it. About the hands-on will be organized for those that are using the virtual machine. They will be organized. Oh, sorry, this stuff is. They will be organized in. Sorry, for those using the virtual machine, the hands-on will be organized in days. So you will find the material of each of the hands-on in these directories, day 1, day 2, and so on and so forth. For those that instead I are not using the virtual machine, the exercises can be all found in this Git repository that is on GitLab. This is the address of the GitLab repository. It's a little bit long, so I don't know whether you can read it or not. But it is available also on the ICTP webpage, so you can take it from there. And okay. To do the exercises of day 1, we just have, for those using the virtual machine, we have to go to the directory QE 2021 day 1, or just from the virtual machine, you just from the virtual machine you. From the virtual machine, you just go to sorry, there is a little bit of a mess with Zoom, and from the virtual machine, you just go to you go to the desktop of you go to the desktop of the virtual machine. You just go to select day 1, and here on day 1 you open a terminal in this way, and so you will be in day 1 directory. And so we start with the first exercise, that is example 01 query compilation. The exercise is pretty simple. You have just to you will find in the directory the archive with the latest release of Quantum ESPRESSO, this file here. And you just have to extract it with the tar command. After you have extracted the file, you just go into the directory and okay. In the directory, you will also find a file called install.md that has all the instructions for compiling the code and configuring and compiling the code in most of the machines, and for using most of the libraries that you want to link that. But today we'll keep things simple, and we'll use just the basic configuration, and using the virtual machine, we have everything that we need for compiling Quantum ESPRESSO already installed in the virtual machine. So we just need to run the command configure, and the configure script will find all the needed libraries, all the needed configurations, and will write them in this file that is called make.inc. And you can check that the file has, first of all, found the MPI library, and has found the FFTW library. And so the program will compile with the MPI parallelism enabled and linking the FFTW3 library. Other things that you may check is the fact that the program has found the library, the BLAS LAPACK libraries installed inside the system. Otherwise, the program will try to compile the internal ones. That is usually not something that. Sorry, I will slow down. Yes. We'll find the libraries, the LAPACK and the BLAS libraries that can be found in the virtual machine. Otherwise, the program will try to compile LAPACK and BLAS libraries, and the compilation will take much more time. So we have now typed configure. I will retype it for who has not seen it. And running configure, the program finds all the instruction, all the settings. At this point, we just compile PW, and so the command for compiling PW is just make PW. Okay, you don't need to configure. You don't need to configure MPI because in this machine MPI is already being configured. So you don't need to configure anything. The program will find the MPI already there. Usually, if MPI is installed in one of the standard paths, but the autoconf script looks for it, you will find the program, the configure script will be able to find the MPI and use it automatically. So you don't have to enable that. There may be some cases when instead you want to avoid to compile the program with the MPI parallelism enabled, and so you have to instruct the program not to use MPI. And yes, okay. I think that we are using a system where MPI is already installed, but if you don't, obviously installing MPI is a little bit more complicated, a little bit longer to explain and during the exercise. And okay, there's no need to do the hands-on right now. I mean, I'm just showing you how to do the exercise, and then you will have time afterwards to do the exercise. And for any questions, please ask to the tutors that will be waiting for you in the breakout rooms. So more detailed questions about anything about this compilation and about the other exercises will be explained afterwards by the tutors. Okay, so it's taking a little bit longer than usually because there is Zoom working on the machine, but I think it's going to end now. So it's taking a little bit more time than usually because there is Zoom that is slowing down all the stuff, but it should be. Okay. So the program has finished, has compiled everything eventually, and you will find all the executables that have been compiled in the bin directory here. As you can see, these are links to the executables that are still in the source directory, and it has compiled not only pw.x, but it also compiled other programs that are used, that are tools that are used by users of Quantum ESPRESSO, and okay, this is the first exercise. Then now we move to the actual actual exercises of computations, and there will be two exercises. There will be two other exercises that will be of actual compilation with Quantum ESPRESSO. Let's see the first one. The first one is example1.benzene. Okay, I already ran it yesterday, so the directory is a little bit dirty. But so what we need to do here is to we have already we have the okay. Let me. Okay, we will find in the benzene directory already the input files for running the exercise. But whenever you want to write an input file of Quantum ESPRESSO, you have to write a file like this. In the virtual machine, there are two tools that are very important, that are very helpful for writing an input file. One is the Emacs mode. One is the Emacs mode. So you open the file with Emacs, and inside Emacs you have activated the Emacs modes that allows you that have the automatic highlighting for for the keywords of Quantum ESPRESSO, and so you can see that everything is already set up. And in case you want to add any variable, you have also the possibility to add it directly, for example, using the command, using the shortcuts of the Emacs modes. Like, for example, for any variable, you can do like this. And then there is the auto completion, so you can use the tab to auto complete the command, and the Emacs will already tell you what command, what is the right name of the variable, and it will ask you for the value of out dir. In this case, we don't want to set out dir actually, so we avoid to. We want to write it, but okay, it doesn't. I will put a variable for a value for that. Put this value. Okay, we don't want actually this value because we have already set up an input and default value, the default value for the out dir, so we don't want to use it. So we go out. Another tool for editing the files, the input files of Quantum ESPRESSO is the PW GUI utility. This is this instead is a graphical user interface and allows you to open directly files, the input files like this. For example, you want to open the input file of Quantum of PW, and you open the file, and the program reads the file, reads the settings in the file, and you can select directly the values with the instructions, and it's a little bit, maybe it's easier to use it than just editing directly the text. So you have a tab for each of the possible name lists of the input of Quantum ESPRESSO of PW. So for example, you have control, system, and electrons, ions, and all the others. And okay, you can play around with them afterwards. Okay, the first exercise, so it consists on first, okay, you will find here the exercise consists first in running the self-consistent calculation for the benzene. So you just run like this. Okay, sorry. And when the calculation is finished, you can look at the output of the program that is here. That the program check that the compilation, that the run is terminated. At this point, okay, at this point you can run the post-processing utility pp.x in order to at this point we run the post-processing utility. I will open it with PW GUI. I will open the input file with PW GUI and show you. So you see, you have in the input file you have the name of the prefix. This is the same. The name of the prefix, that is benzene, like it was for the self-consistent calculation. Then you have to specify the name of the output file, that is in this case is psi square benzene, and then you have to choose the functionalities, the post-processing utility that you want to run. In this case, we want to run psi square, that is the utility that computes the charge density related to a single molecular Kohn-Sham orbital, and so it computes and we are using and so you just select this one here, and if we look directly at the file, we see that we have the prefix specified as benzene. You have to specify the name of the plot of the file here. You have to choose the plot num. This is the one that chooses you that tells the program to compute psi square. Then obviously in this case we are doing a calculation only at gamma, so we have only one K point. We want to use all the orbitals, so we just go from the first to the 16th orbital, and we select L sign equal true. L sign equal true means that as we are running a molecule, and we are our Kohn-Sham orbitals are real functions. So the only difference in the phase is due to the of the sign. So the program will not only compute the charge density related to the orbital, but will also give the local value, the value of the sign of the function in that point. And the point, then there are two name lists. One is input PP, where we tell the program what compute, and then we have another name list that is called plot. That instead tells the program how to print out the results. Here we have we specify the type of output that we want to use, that we want to have in output. So we have .xf means that the program will print out an output for x Christen. If flag equal 3 means that we provide us with a three-dimensional data file. Then we have that we are going to plot only one file. Then here we specify the output format that is 5, that is related to x Christen. And okay, in this case we have only one file, so we are not combining densities from many files. But in any case, you can when you combine many files, then these files may be summed, and each file has an individual weight in the sum. In this case, having only one file, obviously the sum is the weight of the only one file is 1.0. So now we run the pp.x. First, it computes the density, then it prints out in file. So the command, the instructions for running the exercise are here. I mean, if you miss any passage, just open the file. Called README. If you open it with Firefox, it's easier because it's formatted with a markdown syntax, and so you can find here all the commands. So the first command is running pw. The second command is running pp.x. This is the one that I just typed, and it's pp.x, and then in input pp benzene, the input of the benzene calculation, and just that, and then here are the other commands. And okay, at this point we have run pp.x, and we have produced the files with the charge density of each of the orbitals, and we have that. We have produced the files in two formats. One is the format that is internal to the post-processing utility, and it has its own format. And then we have also the format that is instead the one that we use to the one that will be used to plot the density files with x Christen. So x Christen is already installed in the virtual machine, so we just have to run so I have to remember the syntax now as usual. We just run x Christen. We run the command x Christen in this way. So we say --xf is an option to specify the program that we are going to read. We're going to read an XS file. and so with the XSF format. Okay, let me show you just briefly the XSF format in the terminal. So it's so the file contains the information about the primitive cell of the structure, then the coordinates of the atoms, and then there are these data grids. Data grids are the data that we want that can be plotted. In this case, is the charge density of one orbital, and there are all the informations to for reading and plotting it. So we just use the excretion in this way, minus XSF. Okay, the program opens the structure, and first it just plots. And first it just plots the atoms, the structure of the atoms. Then at this point we want to see we want to plot the data grid with the charge density. We go in tools, that is here. Okay, we have just here the various menus. We select the tools menu. We select data grid, and here in data grid we have we can select the different data grids. We have one only data grid, so we just select this one by default. And here there is a multiply factor, as the charge density is divided by the volume of the cell. So as the total charge is divided by the volume of the cell, it's printed in electrons per cell, and so it's very small because your cell is large, as your system is in this case we were computing an isolated molecule, so we're using a very large, a relatively large supercell where the graphene, you can see it, you can see it here. We are using a supercell, so we have the benzene molecule that is at the center of a large supercell, and it's allegedly isolated by the periodic images that you can that you can actually print if you want. If you want, you can show like this. You see, now they are isolated one from the other, so but they are one far away from the other. But in doing this, we are obviously using a very large supercell, so the value of the density is very small. So when we use tools and then data grid to import, okay, why not? Okay, just when it doesn't work. When we import the data grid here, we need to have to avoid to have very small values. We can multiply this value for some multiplier. In this case, I use 100. So, and I just import it like this. And here, the program shows you a menu where it tells you that here you have in this, you see the, you can see the oops. So okay, here in this. So let me. Okay, here, as you can see, here you have now I can see the Now you can see in the panel you have in the panel it shows you which is the minimum value of the charge density and the maximum values of the charge density. So you need to select a value between these two in order to show an isosurface. Just put here 0.3 just for trying, and we select here render ISO value in order to have that the program also prints the sign of the charge density. We just submit, and as you can see, you have it plots you the charge density. One other thing that you can do is then you can try different values to see which is the one that it's better for you. So you see the and then you can after done this, you can customize the image. You can, for example, select a different color for the background, like for example, white. In this case, we don't need the supercell. So here in display, we can also select we can avoid to use the crystal to show the crystal cell. So if you select here, there, you can delete the crystal cell from there. Once the orientation of the crystal is when you have chosen a good orientation of the crystal, one other thing that you can do is select a tessellation factor that is better than 30 in order to have a better quality of the image. For example, we can use something like 70. And we can, other thing that we can do is just to select anti-aliasing to improve the quality of the image. Once we have done these things, one thing, as we have 16 orbitals here, and we want to do the same customization of the image for all the orbitals, we can save the status of the molecule. We can save it in this file, in a file that is called, that we can call as we like. In this case, I will call it a MO state excretion, and then I will save it. Okay, the file already exists, but I just rewrite it. At this point, we can close this file, for example, and okay. For example, if we want to plot another orbital, for example, 12, using the same settings as before, we can use the option -- script and use the script that we saved, that we have just saved, like this, and the program just reads the instructions, uses the same settings that you were using before, and prints the file like this. And that's it. Okay, during the hands-on, you will also find here a script called plot psi_square.sh that allows you to plot and save all the images in a PNG format. If you want to learn more about how to use XCRIS, then it's a good thing to see the example in this image. And just that. Now let's go to the second exercise, which is graphene. Before running graphene exercise, I changed the exercise I changed some things in the exercise yesterday night. So please, to download the last settings, just do git pull like this. Okay, in my case, obviously it says already up to date because I already saved the exercises there, but just do git pull to update everything in order to have the exercises as I'm going to describe you. Okay, also in this case, we have that we have various input files. The first input file is for the SCF calculation. So you can see here the exercise, you can see here the input file. As I was saying before, you need to specify a prefix. You need to specify which type of calculation are you doing, and in principle, you have also to specify an out-dir you need also to specify an out-dir and a pseudo-dir. Actually, in this case, we don't need to specify them just because they have been defined as environment variables. Virtual machine. So you have specified in the virtual machine two environment variables. One is espresso temp dir and espresso pseudo. Whenever we don't specify in input, here in the input, the values of out-dir and pseudo-dir, the program will look for these two environment variables and will set the out-dir variable to espresso temp dir and the value of pseudo-dir to the value of espresso pseudo. So in calculations that are done in places where you have not set up these two variables, it's important that you specify here the value, the name of the out-dir and of the pseudo-dir. So again, looking at in system here, we have also the description of the system. The system is described by a IBRAV index that tells you which crystal structure you are using. In this case, IBRAV equal 4 means that we are using, for example, the hexagonal structure. And then these are the dimension of the structure, the number of the atoms, the number of types of atoms used in the cell. And here we are specifying the cutoff energy for the basis set and the cutoff energy for the density basis set. Other things that I can show you are here. We have the coordinates of the atoms that we are using and the mesh of the key points that we are using. As you can see here, the hexagonal lattice constants have two main dimensions. The first dimension is the dimension of the lattice parameter on the plane, that is the length of, if you wish, of the hexagon. And then this one is the ratio between the height of the cell and the in plane lattice parameter. As you can see here, it's put to 3. It's put to 3 in order to assure, to warrant that we have enough distance between the graphene sheets and that they don't interact, in order to simulate in this way a two-dimensional system using periodic boundary condition. At this point, we can run in pw.x. Yes. Okay. Calculation is very fast, just runs and prints out the output. Okay, after we have, okay, there is a raised hand. Please, can you, I don't know if it's possible I think it's not.
Good morning, sir.
Yes.
I just have one question. We do the exercise on the same time at the same time than you, or we do it?
No. It's, you can do also afterwards in the session, and just going to.
Thank you.
Okay. There's no problem to. No, there is no need to follow me right now.
Thank you, sir.
And okay. Once we have run the self-consistent calculation, we need to we will run a non-self-consistent calculation, and okay, the input for the non-self-consistent calculation is practically the same as the one for the self-consistent one. The only things that will be changing will be that here we'll be using an SCF instead of SCF. That means non-self-consistent calculation. And the other thing that is changing is that as we want to use the eigenvalues computed in this calculation to compute the density of states, and the density of states, we will use a denser mesh of key points. So it will be 12, 12, 1 instead of 9. And the other thing that we are going to change is the way in which we compute the occupations. If we look at the previous file, you will look at the previous file, you will see that occupation was not specified. So that means that occupations that we use the fixed occupations, and we use fixed occupations, while instead in this case we are using tetrahedral occupation. Why we are using tetrahedral occupation? Because for computing the density of states, we need to we need a more precise method to compute the occupations, and then you can see it will be different, and let's do that. So we now get the question is also very fast, and once we have computed the non-self-consistent calculation, you can use the DOS program to compute the density of states of the system. The input of the DOS program is this one. It's very simple. You just need to specify the prefix that has to be always the same as before. So that must be prefix equal graphene 1 times 1 PBE, and the name of the DOS file that you want to input, that you want to print out in output. And you will read all the settings of the systems from the previous runs from the previous PW runs. So the calculation is just DOS.x minus E DOS.graphene routine. And the program produces a file that is called graphene.dos. In graphene.dos, you will find two things. First thing that you have to notice that you have the value of the Fermi energy. And then you have the density of states. Then you have the density of states and the integrated density of states. This is the value of the density of states, and sorry, this is the value of the integral of the density of states, and this is the integral of the density of states. And okay, for plotting it, we have prepared an input. We have prepared a script that is called dos.gp. Okay, the first thing that if you open the input, you will find that here you have 0.0. So you have to put here, instead of 0.0, you have to put here the value of the energy of the Fermi energy that you have found in the DOS file. And yes, the structure was already optimized. I think that we were using the experimental structure. I mean, this is not an example about how to optimize the structure. So we just took a structure that was already optimal, and we just use it as an example. I mean, no, I don't know whether the value of the lattice constant is optimal. I guess it is, but I don't know. If you are curious about that, okay, let me see. Okay, first let's plot the DOS. So now, if you want to plot, okay, you can just look at the pw.graphene.scf.out, and okay, if you're curious about if the structure was already optimized or not, one thing that you can do is take the input file of pw.x, the SCF file, and add here this flag tprn4 as set to true. What the program does in this way is just to then we just rerun the program. Just rerun the program, and at the end of the program, you will have that forces printed out. But actually, the point is that in this case, the system obviously is symmetric, so the forces are vanishing by default. So you need to optimize the lattice constant in this case, and obviously I don't know whether it was optimized or not. And so the other thing that you can do is to try to optimize, to check a different lattice constant and see what happens. But this is an example that we'll do tomorrow with other systems, but then you can obviously adapt them to graphene. And okay, now we want just to plot the DOS. We have prepared the script, and now we plot just the script like this. And the program shows you the output, shows you the DOS. So okay, the part that is filled is the part up to the Fermi energy. The part that is remains unfilled is instead for the valence band that are not that are not filled. I've set out, okay, let me show you again the, sorry, stuff is, so again, when the plotting script makes two things. First thing, the plotting script does two things. The first thing that the plotting script does is to shift the energy values in order that that the zero is at Fermi energy, and just that. So in this case, when you see the plot, you see that sorry, you see that the Fermi energy is set at 0 equally, while instead, okay, this is obviously in the, if you look at the DOS file, if you look at the DOS file, sorry, if you look at the yes, at the DOS file, you'll find that the value of the Fermi energy that you had at the end of the DOS file was 0.92. So we are just shifting the energy in order for plotting the density of states with the Fermi energy at 0. Okay, the second part of the exercise is plotting the bands of graphene. So now we have to run another W calculation. In this case, we select as calculation bands. The input is always the same because the program must read the density of the charge density from the same file as before. In this case, we don't specify occupations because we are computing the bands, but we specify the number of bands because by default, the program uses as occupation fixed, but when you use fixed as occupation, only the occupied bands are computed, and so if we want to compute also the valence, the conduction bands of graphene, we need to specify more bands than the 4 bands that are occupied in graphene. So we now run the calculation. Also, this calculation is very fast. And then we run another post-processing utility that is called bands.x. And use the input that is already being prepared. Also, this input is very simple. It just contains, again, the prefix that is important because you need to the prefix because it instructs the program where to read all the data from PW. Then you have to specify the number of the file that you want to write. And here we also specify LSIM equal to, that means that the program will, that bands.x will make the symmetry analysis of the bands. Just run bands.x. And again, you see we have specified LSIM equal true, and and so the program makes the symmetry analysis at each point. So it prints you the symmetry analysis of all the eigenvalues of the bands that you have computed. And if you are looking for something that is symmetry related, this is the file that you have to look. At this point, we have we want to plot the bands. To plot the bands, we have created another new plot script that is called spaghetti.gp. Again, here in the file that you have in your directory, this value is still set to 0, and you have to set it to the same value of the Fermi energy that you will find in the DOS file. Then you have to uncomment this line that here is already uncommented, that will set the axis of the will plot the 0 axis in order to show you where the Fermi energy is, and then the script runs. The script just reads the file called graphene.bands.data.gnu and just takes the values, shifts them of the Fermi energy in order that the Fermi energy is plotted at 0, and plots everything like this. And we have also set here the ticks to the I symmetry points in the Brillouin zone. You need just to run it, and like this. And here you have your bands, and as you can see here, there is the Dirac point, and this is the exercise, and that's it. And okay, there is one more thing that I wanted to say. And okay, for example, okay, in this case, the path of the okay, we'll show you the slide directly. It's better. Okay, there are two tools for creating the Brillouin zone that I wanted to talk to you. I mean, in our case, in this case, the plot of the Brillouin, the key points for the path for the band plot were already set in the input, so you don't have to create it. But and there are two tools for creating it. One is the key path selection tool of XCrisden, and the other one is one that you can find online in materialscloud.org tools seek path, and that also allows you to create a path. That okay. First thing, this tool suggests you a path that is the path that is usually used is used as a standard, and then gives you the coordinate and helps you to write the input file. And I think that's it. Sorry if it was a little bit confusing, the presentation. It's just that I had a problem with sharing the screen, and it was I almost couldn't see anything of what I was presenting, so I'm sorry. If there are any questions, otherwise...
Yeah, there are several questions from the streaming. If you can look them in the chat, I posted it for you.
Okay. Okay, yes, 0.920. Okay, the first question is, yes, you need to do the NSCF before doing the DOS.x or project.x. Okay, it's not mandatory. You can also use the eigenvalues that you have computed with the self-consistent calculation, but usually when you do the self-consistent calculation, you use a key point mesh that is good for doing an accurate self-consistent calculation, but then when you want to plot the DOS, for the quality of the DOS, you may need a finer mesh. The other thing is that, for example, in this case, for doing the density of states of the project density of states, we want to use the tetrahedral method. Why we want to use the tetrahedral method? Because, well, the CF calculation just tries to compute accurately various integrals in the Brillouin zone. When you are plotting a density of states you are actually plotting all your functions are much more much sharper, so they will require a much more denser number of key points, and also techniques like the smearing technique or just the field sum with the Monco-SPAC are not accurate enough, because they just try to take away the integration of the periodic part of, for example, in this case of your eigenvalues. In the other case, instead, you have something that is much more localized in values. So, for example, when you do a density of states, you have the calculation of your band times step function that is very, very sharp and cannot be done with cannot be done accurately with the other techniques. So yes, in principle, you can use directly the SCF, but the result that you get is qualitatively not the same. It's not so good. So it's always better to have first a non-self-consistent calculation then a non-self-consistent one. It says it's better to use IBRAV. Let me see, but I don't understand why it's okay. Every time I run the code, it says it's better to use IBRAV. Yes, it's true, and because when you specify an IBRAV vector, then what happens is that the lattice is generated by Quantum ESPRESSO itself. So all the symmetry analysis is made easier, and it's a little bit it's more protected, it's safer. While instead, when you use IBRAV equals 0, what happens is that you have to specify the lattice vectors, and then it all depends on how many digits you are using in specifying the lattice vectors. It depends on how these, if the orientation of these lattice vectors is compatible with the symmetry analysis of PW. It should be, but as orientations are infinite, we actually never know exactly what may happen, and especially when you run first a calculation with PW, and then you want to use this information to run a phone calculation, it's much more safer if you specify the IBRAV, if you have an IBRAV that is correctly done. I mean, sometimes one needs to specify instead the lattice vectors, then you can also use those ones and just take the warning, and if you know what you are doing, it's also okay not to use IBRAV. Then, so the structure was not already optimized. Okay, this one has already answered. So yes, how should we decide if to describe the structure using IBRAV equals 0 or specifying the IBRAV? Okay. Now, in the case of graphene, as I showed you, there is no need to do the relax calculation, because by symmetry the forces are 0. What you may need to do is to compute to check that the lattice constant is the one that minimizes the structure. But okay, this was not the scope of the exercise. In this case, the exercise, we just took a value of the lattice constant that is close to the experimental one, and with this one we just wanted to show you how to compute the density of states and the bands. Yes, in principle, obviously you may want to use an optimized lattice constant, even if in many cases, when you are computing quantities that depend on the lattice constant, in many cases, if the DFT doesn't give you a very accurate value of the lattice constant, it may also be useful to use directly the experimental lattice constant. Also, in this case, is something that depends from case to case, and one has to, if he knows what he's doing, he can decide by himself. Then okay, as I was saying, why, okay, here there is another question. In PWSCF data out, we found 0.9202 for the density of states, and instead when we do graphene DOS file, we find 0.9207. Okay, the difference is not that large in this case, but as I was saying, we were using two different techniques to compute the density of states, and two different key point mesh. The most accurate is the key point mesh. The most accurate is the value of the Fermi level. And so yes, there is some slight change, and so the most accurate you are, the better it is, even if in this case, I mean, the difference is very small, 0.9202 and 0.9207, that are practically the same. Okay, so there are other questions in the Slack channel that I still haven't opened, and yes, you can do a spin component projected band structure plot. We will show something like this in the day of magnetism, actually. So we will, okay, it will be a day 7. So you have just to wait. I mean, if you are very curious, you can also go directly to the exercises in day 7 and see how it's done there. And otherwise, just wait for the tutorial that day. And what else? Okay, sorry, the Slack is taking some time to open. It will take a long time to open. Why? I don't understand. Okay, day 1. Okay, you don't. Okay, there are a lot of questions in the. Okay, sorry, I shouldn't have. Actually, yes, it's There are really a lot of questions.
Pietro, but you don't need to do the Slack answer from here. I mean, we do
okay. I will answer. I will try to answer the question afterwards.
Yeah, we do it.
Okay, just to start doing the exercise because I've run very late and I was a little bit too long about what I mean. Yesterday I tried the presentation. It was much faster, and today instead it was a kind of complete confusion. Sorry. So I think that you can start doing the calculation. I will try to answer the questions in Slack now, and I think it's. I can stop sharing the screen now, and yes, okay. I think it's everything for now.
Yeah, if somebody lost most of the steps or some like generic trouble, they can join the breakout room with the
tutors,
like one-to-one help.
Okay, I will start answering the question on the Slack now, and
yeah, if there are no, yeah, we can close the
session. Okay.
No, not the session. We can close the streaming session. We can remain available here for the people in Zoom.
Okay.
Maybe